Thank you very much for the invitation and for the introduction. Okay, so it's given that the audience is not necessarily familiar with GR, I will start slowly, and I will in particular introduce the main equation. So I apologize for experts, because this is I have targeted this talk rather for non-experts. Okay, so let me start with the Einstein equations in the vacuum, and in particular the corresponding evolution problem. So the main object will always be a Lorentzian manifold. So the manifold M has dimension 4, 1 for time, 3 for space. And the signature of my metric, it's a Lorentzian metric, so the signature will be minus, plus, plus, plus. And let me immediately give you the simplest example, which is the flat case, which is the Minkowski spacetime. So M is R1 plus 3. And the Minkowski metric is given in Cartesian coordinates by minus dt squared plus dx1 squared plus dx2 squared plus dx3 squared. Okay, so the Einstein equations are equations on, the gravity according to Einstein manifests itself in the curvature of the spacetime. So I need an object to measure the curvature. So this will be the curvature tensor. So let me not tell you what it is. It's a complicated expression, but let me just say that the curvature tensor is a 4 tensor. So here my Greek indices will be always running from 0 to 3 for the 4 dimensions. And this 4 tensor, no matter what it is, if you want, tells you everything you want to know about the curvature, and you can think of it as a distance to Minkowski. Minkowski has a 0 curvature tensor, and if you have a non-zero curvature tensor, it's a measure of how far you are from Minkowski. Okay, but now this tensor, you can take a trace of it. So I very much like matrices, I can contract the first and the third index, and I will get a tensor with only 2 indices. And if I contract it, I'll get just the Ricci tensor. And this one is left, well, okay, with this notation, let me write like this. So I contracted the first and the third indices. I get a symmetric 2 tensor, the Ricci tensor. And with this tensor, I can write down the Einstein vacuum equation. So curvature tensor has all the information on the curvature. The Ricci tensor has only partial information. And the Einstein equations in the vacuum are simply given by Lorentzian manifolds with a vanishing Ricci tensor. Okay, so under this form is still mysterious, so I'm going to write it in a more explicit way for the purpose of the talk. But first of all, let me mention one first property of solutions of the equations. It turns out that if you take a metric, if you put any solution of the Einstein equations and you pull it back by any diffeomorphism, then you get a new metric, and it is a gain solution of the Einstein equations. Okay, so that means that out of one solution, you can produce infinitely many solutions, as many as diffeomorphism. And of course, it's natural to consider that it's exactly the same object. Okay, so this is why this is the principle of general covariance. You, in fact, don't look at solutions, but rather class of equivalence of solutions modulo diffeomorphism. In other words, you identify these 2 solutions here. Okay, and on a more practical level for us, it means that you have the freedom to choose coordinates. So let me immediately take a particular coordinate system, which is not the one, in fact, that I'll be using in the proof I'll explain. It's just for the purpose of writing it in a very simple way. Okay, so these coordinates are called wave coordinates, but it's not too important. What is important is that in this coordinate system, you can rewrite the Einstein equations as a coupled system of 10 quasi-linear wave equations in the coefficients of the metric. Okay, the metric is a symmetric tensor in dimension 4, so it has 10 independent components. So it gives you a coupled system of 10 nonlinear equations. The nonlinearity gives you the coupling. It depends on the metric and first order derivative of the metric. And on the left-hand side, you have the quasi-linear feature, because the D'Alembert itself depends on the metric, which is the unknown of the problem. Okay, so under this form, it's clearly an evolution problem. And in particular, you can look at local existence and uniqueness. So the local existence statement is due to the seminal work of Yvonne Choquet-Bruard, the local existence and uniqueness. And the concept of maximal solution is due to Choquet-Bruard and Garrosh. Okay, so there exists, if you have suitable initial data for Einstein vacuum equations, in particular sufficiently smooth, then you are locally well posed, and there exists a unique maximal solution. Okay, so here what I want to look at, the stability of a particular stationary solution, or rather a family of stationary solutions. So you have already one on this slide. Obviously, the Minkowski spacetime is flat, so the curvature tensor is 0, and therefore the Ricci tensor is 0. So that's already a first solution of the Einstein vacuum equations. If you want, it's the trivial solution for these equations. And what I want to look at is a different family of, is a different stationary solution, or rather family of stationary solutions. And let me present them now. So this is the Kerr family of solutions. And in fact, it turns out that they contain, as a subfamily, the Schwarzschild solutions, which were found much earlier. Okay? So let me start with Kerr, even though, of course, historically, Schwarzschild was found much earlier. So the Kerr here is, so here I'm going to write this family of solutions in the so-called Breuer-Lindquist coordinates, which are simply the spherical coordinates of R1 plus 3. Okay? In this case, you get the following formula, which is a bit intimidating, but fortunately, it's not relevant for the talk. What is relevant is, first of all, that there is a formula, which means these are explicit solutions. Second, that they depend on two parameters. So it's a two-parameter family of solutions. So here, A and M, if you want, you should think of M. So these will be, I'll explain, these are black hole solutions. So, I mean, they contain black holes. So we'll see in the next slide. So here, M is proportional to a mass. So it's proportional to the mass of your black hole. And A, or rather M times A, is proportional to the angular momentum of your black hole. So it's a rotating black hole. Okay, but we'll see this in the next slide. For now, let me just say it's a two-parameter family solution. And if you look at the metric coefficients, even though they are pretty complicated, they are only functions of r and theta, okay, which means they do not depend on the coordinate t and on the coordinate phi, which means that Kerr is stationary, dt is scaling, and its axis symmetric, d by d phi is scaling. In particular, indeed, this is a family of stationary solutions, as I advertised in the previous slide. Okay, now I can let me still look at the particular case where the angular momentum is 0, because then you recover the Schwarzschild metrics, which were found much earlier, which are more symmetric. In fact, they are strictly symmetric, and they have a much simpler formula in this particular case, even though the formula itself also is not too relevant for the talk, except for the two remarks I'm going to do now. So if you look at the coefficients in front of dt squared and dr squared, these two metric coefficients here, you can see in particular that when the coordinate r tends to infinity, both coefficients here tend to 1, and you recover the Minkowski metric written in spherical coordinates of R1 plus 3. Okay, so these metrics are asymptotically flat. In other words, they approach Minkowski when the special coordinate r tends to infinity. And in fact, this is also the case of Kerr. So we are in the framework of asymptotically flat solutions. And second, there is a singularity at r is equal to 2m here. So it turns out it's not a true singularity, it's a coordinate singularity. I can change coordinates and get something which is smooth across this hypersurface, but nevertheless, it singles out an important phenomenon, and precisely this is connected to the fact that these spacetimes contain black holes. A black hole, well, one black hole in fact. These are black hole spacetimes. So more specifically, Schwarzschild spacetimes correspond to the particular case of non-rotating black holes, while Kerr, under the restriction that, the physical restriction that absolute value of A is less or equal to M, then Kerr spacetime correspond to rotating black holes. Okay, so let me maybe explain for non-experts in one slide what it means to be a black hole, and I'll do it in the particular case of Schwarzschild, but I claim that for Kerr it's exactly the same. So here I apologize to experts. I'm not going to draw a Penrose diagram because I know that it can be confusing for non-experts. So let me simply draw things in the TR coordinates, which means that because Schwarzschild is spherically symmetric, any point on this picture is in fact a two-sphere. Okay? And I want to look at the so-called causal structure. In other words, I simply want to draw light cones at different places in my space. So let me start with very large R. If R is very large, I'm asymptotically flat. I look like Minkowski, and I recover the light cone, the standard light cones of Minkowski. That's how I look like. But of course, once R decreases, you go further and further, you drift further and further away from Minkowski until, and your light cones as a consequence are going to tilt to the left. And there will be so much tilted to the left that when you cross when you are at the hypersurface R is equal to 2m, you're actually tangent to it. Okay, which means that if I look now at the trajectory of lights, which would follow the light cone, you see that they all point inside this region R strictly less than 2m, which means that light cannot escape from this region, and this is exactly what it means to be a black hole. Okay? Okay, so R strictly less than 2m is the black hole in Schwarzschild, and R is equal to 2m is the event horizon. That means it's really the boundary of what you can expect to see if you, as an are outside of the black hole, which is supposed to be our case, right? We are outside observers, and this is the boundary of what we can see. Okay, so for Kerr, it's exactly the same picture, except that you have to modify this value of R. So let me not do it, but it was just to have a representation of what a black hole is. And now I can finally state the stability conjecture for the Kerr family. So let me recall that we're in the context of asymptotically flat solutions to Einstein vacuum equations. And then you have the following conjecture, which first of all, you should notice that this is not the stability of the entire family, but just of the exterior region, which is the exterior of the black hole. Okay? So the interior of the Kerr black hole, on the other hand, is expected to be unstable. Okay, and then the statement is that if you take a small perturbation of a given initial condition of an exterior Kerr under the so-called subextremal restriction, so absolute value of A is strictly less than M, then your solution is global, it's globally close to Kerr, and it converges in the limit to another member of the Kerr family with a different, a priori, in general, a different final mass and final angular momentum. And of course, tracking the final parameters is part of the problem. Okay, let me make a connection with, in fact, the first stability result in this field, which is the stability of the Minkowski spacetime due to the monumental work of Kusurin and Kleinemann. So if you want, that's the stability of the flat solution. And here, this conjecture is about the stability of black hole solutions. Okay, so what I want to do from now on is explain, I want to review the history of the problem. I'll try to emphasize a little bit more what happens with the wave equation, because I think it's probably more relevant for this audience. And then I'll state a result, and finally, if we have some time, I'll discuss some elements of the proof. Okay, so let me start, as it's usual in the stability problem. I look at the stability of a given solution, so I want to look at the linearized operator around this solution. And in this case, well, okay, I often refer to it as the linearized gravity system in this context, when you linearize the Einstein equations around a Kerr solution. And here, in other words, I write my metric, which is a perturbation of Kerr, as Kerr plus a small perturbation. At this stage in linear theory, I forget that the mass and the angular momentum change. I just write it like this. And then I linearize the Einstein equations. And here I'm going to only write it in this schematic form. I don't want to discuss any gauge choices at linear level. So let me just write it like this. It's in other words, it's the variation of the first variation of the Ricci tensor at the Kerr metric on H. And I'm looking at this coupled system of equations at this stage. Given the gauge I gave you earlier, you can think of it as a coupled system of wave equations on Kerr with first and zero order terms. Okay, so you have a large coupled system of wave equations. It's not the gauge in which I look at it. It's not the gauge in which I consider this problem, but it's a good way to represent yourself this system. Okay, so there was an intense physics literature on this problem from the 50s to the 80s. And here there are many references. I'm only mentioning the names that will pop up again in my talk. So there is the name of Roger Wheeler, Tucholsky, Chandrasekhar, and Whiting. And I apologize because there are in fact many more contributions, but these are the ones that will come later in the talk. Okay, let me maybe, for reference, give you an idea of what happens if you look at stability of Minkowski. If you look at stability of Minkowski, you expect to have a large coupled system of tensorial equations, but for some reason, because you are around the flat case, there is a drastic simplification, and everything reduces, in fact, to just one scalar wave on Minkowski. Okay? But now, if you look at Kerr, if you look at the linearized gravity system in Kerr, then it's quite different. In fact, because of the complexity of the solution, there is no decoupling, and you still have a large and integral system to deal with of tensorial wave equations. Okay, so let me explain a little bit how it was approached in the physics literature, and this starts, well, in fact, it starts much earlier, but let me mention the work of Tucholsky, because this is quite central in the approaches that were followed later. Okay, so what's happening is here, what you should imagine, I have a large coupled system of PDEs, and okay, maybe I'll stay here. Okay, let me draw it here. You have a large coupled system of equations, and of course, so the analogy you can draw is with what you would do if you had a large linear system to solve. So you have a full matrix, and obviously, when you have a large linear system to solve, one very efficient method is to put it in lower triangular form by Gauss method. That you get your lower triangular matrix, and then you solve your linear system from top to bottom. And if you do this, in order to put it in Gauss in this Gauss form, using Gauss method, in this lower triangular form, there has to be at least one component that completely decouples from the rest of the linear system. Okay, And the idea of Tucholsky is precisely to look in this. Of course, now you have a linearized system of, you have a coupled system of PDE, so there is no general principle and absolutely no reason in a priori why it should be true here. But nevertheless, thanks to the structure of the Kerr solution and the Einstein-Bacon equations, Tucholsky was able to find exactly such a quantity. In fact, he found two, which I will denote schematically by psi plus and psi minus, such that these quantities decouple from the system because they satisfy wave equations with no coupling to the rest of the system here. So that's zero. Okay, so here, let me do a couple of remarks. First of all, the Tucholsky scalar here, psi plus minus, they live at the level of the curvature tensor. There are contractions of the curvature tensor with very specific null directions. Let me not, I mean, I could even explicitly write them, but I'm not so sure it's important here. And first, second, you see, in particular, highlighted in red, this first order term. This first order term is responsible for these wave equations being non-conservative. In other words, they do not derive from a Lagrangian. That's actually, that is part of the difficulty of the problem, at least if you follow the techniques I'm going to explain, which are based on the energy method, where you really want to have a Lagrangian and a corresponding energy. Okay, but let me forget about this problem for now, and let me just say that the goal from here, it's pretty clear. You want to derive decay for the Tucholsky quantities based on these Tucholsky wave equations, and then you want to rely on it to derive decay for the rest of the system, provided you are able, indeed, to find a complete lower triangular form for your system. Okay, so maybe let me start, given the title of the conference, I want to talk a bit about wave equations. And in fact, let me start with a simpler case where I don't have zero or low order terms. I just want to talk about, first, to spend a few slides just on the scalar wave. Okay, the scalar wave on Kerr. So in other words, this is the simplest linear model you can think of. Of course, you'll have to go from this to Tucholsky because this is Tucholsky that pops up and not the scalar wave. But it's natural to assume that you have to deal with it first before understanding Tucholsky. Okay, so in this slide, let me explain you what is the relation, what you should understand about the geometry of your spacetime, which is in connection to, which is related to the decay of your linear waves. So there are four important properties here. First of all, there is presence. So the first 2 points are actually bad news. I mean, in other words, difficulties you have to deal with. The first one is the presence of trapped null geodesics. In other words, these are geodesics that will stay forever in a compact region of your spacetime. So why is it a problem? Because, well, I guess for this audience, we all well know that at high frequency, waves propagate along null geodesics. And if you want to get decay, you want these null geodesics either to go to infinity or to fall inside the black hole. And these are geodesics that do neither of those. So these are enemies. Of course, the good news is that this trapping is fairly weak. It's called hyperbolic. Or you can do it still, you can still get decay in the end. The other piece of bad news is super radiance, because you have a killing field, dt. By Noether's theorem, the symmetry implies that there is a conservation law, conserved energy. But now, unlike Minkowski, the energy for the scalar waves in Kerr is not globally positive. It's only positive for R large enough, because dt is only time-like for R large enough. In other words, there is a region, the so-called ergosphere, where the energy has the wrong sign. Okay, this was for the bad news. The good news are the two next points. The redshift region, so this is a tiny neighborhood around the horizon, along which at least things behave well as far as decay is concerned. So this captures a physical phenomenon called the redshift effect. And also for the large R region in your spacetime, because you are asymptotically flat, it's like Minkowski, so at least you're in familiar territory. Okay, so this was for the geometry. Now let me outline the strategy that was found to deal with this. I should mention that there is a very different strategy that came from the work of Hinz and Vashi, and I'll mention it later. But for now, let me explain this strategy based on the energy method. Okay, so first of all, you want to derive decay, quantitative decay, and you want to do it using robust method because, of course, later you think of applying this not to exact Kerr, but to perturbations of Kerr. Okay, the strategy has 3 steps. First, so the first, in fact, most difficult step is to derive energy Moravec's estimates. This was initiated in the work of Blue and Sofer. And well, this is the first, this has to be the first simply because in this scheme, this is the only estimate which is on the causal region. Okay, so you first need to do this estimate on the causal region for the wave equation, and then you can proceed to work on non-causal regions. So you certainly, there is no question that you have to start with this. And why is it the most difficult? Because this is the one that deals with the main enemies, which are trapping and superradiance. Okay, and then you can go to the two good points in the previous slide, which is the fact that near the horizon things are better. So this is, in fact, you can say how to measure how better they are. You can use the redshift estimates introduced by Jansky. So that allows you to deal with some degeneracies in the energy Moravec near the horizon. And then the energy Moravec estimate gives you only weak decay. It's L2 integrable in time. So you want to transfer it to pointwise decay with the decay that you expect. And this pointwise decay, you can in particular derive it by the method, the RP weighted method of the famous Rodiansky, which first of all happens only in the Minkowskian region. And it allows you somehow to first derive weighted estimates in R and then to transfer the decay in R in decay in T to get your correct pointwise decay. Okay, so let's say this was the two-slide summary of how to treat the linear wave equation in Kerr. And let me now go back to Tucholsky. Let me maybe just close this chapter on the linear wave. So what I explained so far was the strategy I outlined for Schwarzschild, but it turns out that the same applied to Kerr later. So it was extended for small angular momentum by Tataro and Toreano using micro-local methods. It was then later reobtained by Anderson Blue using this time physical space method for small angular momentum. And then it was extended to the full range, full subexponential range by the famous Rodiansky and Schlappenthal-Rothman. Okay, so this was what I want to say about the scalar wave, and now let me come back to Tucholsky, which is this more complicated wave equation with first and zero order terms. And the first result I want to mention is this result of Whiting, which tells you that Tucholsky has no exponentially growing modes. Okay, so this is the statement that there are no obvious counterexamples to decay. Okay, but on the other hand, you want much more. What you want is quantitative decay rate for solutions. And again, the difficulty here, at least with the approach I outlined, is the fact that Tucholsky does not derive from a Lagrangian. So what was done, in fact, and this was the breakthrough of the famous Rodiansky, was to realize that you can use a transform due to Chandrasekhar, which in fact transforms solutions to Tucholsky to another equation, which is called Regge-Wheeler. And this equation, found much earlier by Regge-Wheeler, itself does derive from a Lagrangian. Okay, it's a wave equation with a potential with a good sign. It derives from a Lagrangian, and you can get decay for solutions to Regge-Wheeler by adapting the techniques for the scalar wave. Okay, and then of course you need to come back to Tucholsky, so you need to invert this transformation, which you can do, and this is finally how the famous Rodiansky could get the decay of Tucholsky in Schwarzschild. And in fact, let me make a connection with the talk of Claudio and of Jonas. I think if I remember well, Jonas told me at some point that this Chandrasekhar transform is what he calls actually a Darboux transform. Correct. So this is very much connected to Okay, and then you can move from, so then it was extended to Kerr for small angular momentum independently by Ma and also Rodiansky, and then to a full experimental range by independently by Millet and Schlappenthal-Rothman, Teixeira da Costa. And here I should mention that the work of Millet is of a very different type. It does not use this technology. It uses actually a proof by spectral methods, which is in line with the work of Ince and Vacher, and I'll talk about it again later. Okay, let me now close the chapter. So this was what I wanted to say about Tucholsky. I want to come back quickly, just in one slide, on the linearized reality system, so in the full system. And I'll start with the bad news, which is the fact that, in fact, the full linearized reality system, you cannot expect to be able to solve it because there is the presence of a kernel at the linearized level. In other words, where does this kernel come from? Well, this is, I mean, we've seen it in several other talks now, but it's the fact that you don't deal with a single solution, but with a smooth multi-parameter family of solutions. And in particular, you have, also, of course, the parameter A and M, but you have also the fact that you can pull it back by any diffeomorphism. Okay? So this immediately, if you take the variation with respect to your parameters, this immediately implies that the variation with respect to mass, angular momentum, and the Lie derivative of the metric with respect to any vector field is in the kernel of the linearized reality system. And of course, if you take back my analogy with the linear systems, if you have a kernel, you can only solve, a priori, you can only solve the linearized system orthogonally to the kernel. Okay, so you cannot fully solve that problem. On the other hand, of course, at the nonlinear level, you have stability. So what does it mean? It means simply that and this was already connected to many other talks, and everybody's familiar with this. You have to track, this kernel is a manifestation of the fact that you have to track the change in mass, angular momentum, and diffeomorphism, and in particular, you want to track what is the final angular momentum, final mass, and final diffeomorphism in your problem. And here maybe, so this is usually referred as modulation theory, and here an interesting part of this analysis is that here you have to, due to general covariance, you have this huge, so this kernel here is finite dimension, but the kernel due to general covariance is infinite dimension, and therefore you have to do modulation in infinite dimension. It is part of one of the interesting parts of this problem. Okay, and let me finally close the chapter on the linearized system. It was found to be stable in the A0K on Schwarzschild by Defamos Rodiansky, and then later independently extended to the small angular momentum case independently by Anderson, Begdal, Buenma, and by Hefner, Hinz, and Vashi. And again, work of Hefner, Hinz, and Vashi builds on the earlier work of Hinz and Vashi that I will mention now, which is of a very different type. It's using spectral methods. Okay, so this finishes what I wanted to say on the history of the linearized system. Let me maybe briefly mention a bit of nonlinear theory before, of nonlinear models that were looked at before looking at the full problem. And here there are many nonlinear models. I just want to focus on the ones that really solve the Einstein equations, but in a simpler setting. Okay, so there are two ways that you could think of two model problems, at least maybe more, but these are the two that were considered. And the first one was the approach of Andras and Peter, of Hinz and Vashi. So you have Ricci. Instead of looking at Ricci G is equal to 0, now I'm going to modify the equation and look at Ricci G is lambda G with a strictly positive lambda. Okay. So if you do this, so the lambda is the positive, is a cosmological constant. So if you look at the case of positive cosmological constant, you have analog of Kerr, of the Kerr family, which is the Kerr-de Sitter family. And in fact, in the seminal work, Peter and Andras were able to prove the stability of the Kerr-de Sitter family for small angular momentum. And here, what is it that you gain by adding this constant? Well, you gain the fact that linear waves in the asymptotic flat case decay borderline slow. They decay like 1/t, essentially. While in the setting of Kerr-de Sitter, suddenly your waves decay exponentially fast. This allows you to drastically simplify the nonlinear terms. And in fact, the way they obtained the decay was to prove the exponential decay was to exhibit a spectral gap for at the level of the linearized operator. Okay, and now if you want to stay in the framework of the asymptotic flat case, there is another model problem you can consider. And that's the case of looking at the power case A is equal to 0. In other words, you want just to look at the stability of the nonlinear stability of the Schwarzschild family. So here, actually, it's not, unfortunately, it's not a closed problem. In other words, if you are close to Schwarzschild initially, the conjecture tells you that in general, you will move to Kerr with a non-zero angular momentum. If you want really to restrict to the nonlinear stability of Schwarzschild, you need to restrict the class of perturbations in one way or another. So a simple way to do this, and this is the route we chose in the joint work with Sergio Kleinman, is to consider a symmetry which is preserved by the flow and which does not contain Kerr for non-zero angular momentum. So we call this symmetry polarized symmetry. It doesn't really matter here what it is, but at least it allows you to talk about stability of Schwarzschild. And in this joint work with Sergio Kleinman, in fact, this was important for us for the extension to Kerr, because this is where we derived we dealt for the first time with modulation in infinite dimensions. I hope to have the time to talk about it later. In particular, of course, the main part is to deal with general covariance. So we have this procedure called general modulated spheres. Time permits, I'll talk about it later. Okay, and then this was extended to codimension 3 set of initial data by Defamos, Holzager, Rodiansky, and Taylor. Okay, so finally, I can mention the result I wanted to talk about, which is the resolution of the Kerr stability conjecture for slowly rotating Kerr black holes. In other words, we are dealing here with a particular case where the absolute value of A is much less than the mass. Okay. So it relies on several steps. Let me maybe outline these 3 steps and the 5 works that come with it. So first, there is the modulation procedure. So this follows from joint work with two joint works with Sergio Kleinman and a work by my student Dawei Shen. So here, the idea is to extend what we had done previously for Schwarzschild in the symmetry class to general perturbations of Kerr. Okay? Then there is another joint work with Sergio Kleinman, in which in particular we lay out our gauge choices and derive all decay estimates except for the Tucholsky scalars. And finally, there is a last work which is joint with Elena Georgi and Sergio Kleinman, in which we derive a formalism for non-integral structures. Unfortunately, I don't think I will have the time to talk about it, but this is related to the fact that for Kerr with non-zero angular momentum, there are some non-integral structures in the sense of non-integral in the sense of Frobenius. And also, this is the part where we derive all the wave estimates. So everything that has to do with decay for wave equations for psi plus and psi minus, but also the top order energy Moravec estimates. This is why you derive the top order estimates. Okay, so maybe from now on, let me talk a little bit about the proof. So I'll try to give you an overview of the proof, and hopefully maybe I'll have still some few minutes to discuss the modulation procedure. So let me start with the bootstrap. I just want to start slowly with just showing you the bootstrap region. So here again, I apologize to experts. I'm not going to draw a Penrose diagram. I want to stick to my picture in R and T coordinates. So R is like this, T is like this. And so here you should imagine that every point now is not a standard to sphere, is a topological to sphere. It's a closed to surface with the topology of the sphere. You are in perturbations of Kerr, so of course these are not round spheres anymore. Even in Kerr, they are not round spheres. So think of any point here, which is the intersection of these cones here with a level set function R. Think of them as being topological to spheres. Okay, so we are in the context of a bootstrap proof. So I want to show you my bootstrap region, and my bootstrap region starts with this last slice here, which is a hypersurface. And you should think that it's not only it's a hypersurface, but it comes together with a foliation by topological spheres. Okay, and each of these spheres immediately generate a future directed or an outgoing null cone. Okay, and this null cone, you will stop it at a constant value of the function r is equal to r0, which is quite large and far from the event horizon, but fixed. And then, because on this r constant hypersurface, you have foliation by spheres coming from the outgoing null cones, you can initialize ingoing null cones. And this is what allows you to enter the event horizon. And in fact, you'll stop at the value r is equal to r1 immediately after the event horizon. Okay, so here I said earlier that you have stability of the exterior of the black hole. In fact, it turns out that due to the redshift effect, you can also go slightly inside, and that's what we're exploiting here. Okay, and it's quite important because this allows you to never have to deal with the event horizon, which is quite unstable. So what you do is you do the proof in this larger bootstrap spacetime, and then once you have obtained convergence, you come back and realize that indeed there was an event horizon and you covered part of the black hole, but a small part of it. Okay, so here, what is apparent from this picture is once this last slice together with the foliation is chosen, then everything is fixed in this spacetime. My null cones are outgoing null cones and ingoing null cones are completely fixed. So all my choices, in fact, happened here on this last slice. Okay, that means that this is where modulation takes place, and in particular, whatever has to do with general covariance, so the infinite dimensional kernel, infinite dimension modulation takes place in the construction of this last slice. And because you do modulation in infinite dimension, what you should expect is instead of standard ODEs that you do in modulation theory, you should expect to have PDEs to find out this last slice. Okay, so hopefully I can talk a bit about it. Let me now move I'll present the general structure, overall structure of the proof, and then I want to come back to this issue of modulation in infinite dimension to close the talk. Okay, so here is the overall structure of the proof. You have, so the first three steps, first of all, about the even further separation. The first three steps here deal with decay estimates. So you should imagine that you have only, let's say, half the number of derivatives, okay, to close with. So it is typical to, this is the typical scheme in a quasi-linear equation. So for this, these are decay estimates. So it's only for half number of derivatives, and therefore you can lose derivative for these estimates. While step number 4 is about top order energy estimate. So here you want to close your argument without losing derivatives. So for this fourth step here, you cannot afford to lose derivatives, okay? Okay, so let's go through the three first steps, which will look very familiar with the strategy I explained in the linearized setting. So first you want to control, everything starts with controlling the Tucholsky scalars. And these Tucholsky scalars I did not mention, but the reason why you want to start first is because obviously from the analogy of solving to top to bottom in the triangularization of the system, and also because there are gauge, the so-called gauge invariant. In other words, they depend at the linear level, they do not depend on the gauge. At the nonlinear level, they depend only quadratically on the gauge. So at this stage, you don't really need to know anything about the gauge to solve them. So that's the very nice thing about them. Okay, so what is the difference with the linear setting? Well, the linear setting, there are two main differences. First, there is a nonlinear term on the right-hand side, and we know already from stability of Minkowski that it needs to have a very special structure known as the null structure, that you need to exploit the fine cancellations in the nonlinear term. And the other extra work you have to do is the fact that it's a wave equation, not on Kerr, but on perturbation of Kerr. And this is where you will test the robustness of the methods. Okay, so this first step, in fact, even though it's conceptually obvious from what I explained in the linear theory, it's actually probably technically the most involved with the fourth step. So these are the two steps that are done in this joint work with Elena Georgi and Sergiu Kleinemann. Okay, then once you have the Tucholsky scalar, decay for the Tucholsky scalars, then you can proceed to control the rest of the system. And here, this is where you want to exhibit a triangular structure. And then you, in fact, to exhibit this triangular structure, this is where you use the fact that you have decay estimates. So you totally break the structure of the system. You forget that this is a hyperbolic problem. You really start losing derivatives. And in this process of losing derivatives, this is exactly what allows you to derive this triangular structure. And so that you only solve transport equations and elliptic systems in the end. So you totally broke the elliptic structure, hyperbolic structure, sorry. But this allows you to get a triangular structure. And of course, you can do it because these are decay estimates, so you can lose derivative at this stage. Okay? So what you have to solve are, in the end, it turns out you have to solve transport equations along the generators of the ingoing and outgoing null cones. So here I put null cones in quote because, anyway, due to these non-integral structures, they are not quite null cones outside of, perturbations of Kerr, but it doesn't matter too much. And then also you have to solve elliptic systems of Hodge types on what I call these topological two spheres, which is the intersection of the cones with the level sets of the function R. And in fact, you cannot expect to do it as we have seen. This is where you know that there is a kernel at linearized level, so you cannot expect to do this unless you deal with the kernel. And in fact, it turns out that there is a separation. The kernel due to general covariance, you feel it in the transport equations, while the kernel due to A and M, you feel it in the elliptic systems. Okay, so this is where you have to do modulation to deal with these kernels. So concerning the general covariance, I'll explain it in the. I'll explain it in the last slide. So here, this has to do with construction of spheres at infinity, which in fact means constructing these topological spheres that foliate this last slice I was emphasizing in the previous slide. So the last hypersurface of your bootstrap spacetime. And then this is the modulation with respect to A and M. You want to define, so this has to do with the kernel in the elliptic systems. You need to find a good definition of the mass and angular momentum that converge ultimately to the final mass and final angular momentum. And here, let me mention something I did not mention so far. In fact, it's not only about it's not a two-dimensional kernel, it's a four-dimensional kernel. You also have to track the axis of the final Kerr solution. You are in general perturbations of Kerr, there are no symmetries, but as you converge towards the final Kerr, you have to be able to track the direction of the axis of the final Kerr. So it's in fact a four-dimensional kernel. Okay, so this was for decay estimates, where indeed you could lose derivative, and then the last step is about closing the bootstrap argument. So here you cannot lose derivative anymore, because you go all the way to top order derivatives. So here you need to remember that you're dealing with a hyperbolic problem, so you need really to use the hyperbolic structure, and this is where you use energy Moravec, as well as the Maxwell character like of the Bianchi identities, which is the set of equations satisfied by the curvature tensor. Okay, so here it turns out that you also need a kind of triangular structure here, and you get it in a different way. You get it by simply throwing low order terms. You think of an iterative process in which you recover derivatives one by one, so that everything that's low order has been recovered previously, so you can throw it on the right-hand side. And that's how you get, so you also get a triangular structure, even though it's in a different way. Okay, and finally, okay, good. Okay, so let me, so I had also a slide on the non-integral structure, but I was not expecting to have the time. So let me finish just with one slide to explain a little bit this issue of modulation, which again has to do with constructing again, let me repeat that I'll finish by explaining you how you construct this, or at least some ideas on how to construct this last slice. So I will not exactly explain the last slice. I will just explain, in fact, how to construct the spheres that foliate the last slice. Okay, so I'll end up with that. Okay, so again, what is modulation? Modulation is the fact that I want to track the final angular momentum, the final mass, but I also want to track the final diffeomorphism. So you could argue, after all, that Einstein equations are diffeomorphism invariants. So why do you even track the final diffeomorphism? This is because, you know, in any proof, you choose a gauge. So you put yourself in a certain coordinate system. And in this coordinate system, you have a representation of Kerr. And if you don't track the fact that the coordinate system moves, then even though you converge to Kerr, you will not be able to see it because you recognize Kerr in a certain way, but it will be written in different coordinates. So if you really want to recognize Kerr, you want to track this change of coordinates. In other words, you want to track this final diffeomorphism. So what do I call recognizing Kerr in my coordinates? What I want to recognize, in fact, are these two parameter family of spheres, which in Boyle-Lindquist coordinates. So remember, in Boyle-Lindquist coordinates, you have 4 coordinates, t, r, theta, phi. And what I want to track are the spheres of constant t and constant r. So the intersection of the level sets of t and r, that gives me topological spheres. In Schwarzschild, it would simply be the spheres centered at the origin at t with radius r. Okay, so in Kerr it's a bit more general. But certainly, if I look at the level sets of constant t and constant r, I get a 2-parameter family of topological spheres in the Boyle-Lindquist coordinates of Kerr. So the 2 parameters are t and the value of t and r. And what I want to find in my perturbed spacetime is the analog of these spheres. I claim that if I find the analog of these spheres, this will be the spheres that foliate my last slice. So this is what I want to track. So to track it, this is what we do in a 2-joint work with Sergio Kleinerman. We design a procedure to construct a unique 2-parameter family of preferred codimension 2 surfaces in general perturbations of Kerr. Okay, so the idea is, I know what I have to track is a 2-parameter family of spheres, so it's not enough to prove existence of spheres of preferred spheres in my perturbation spacetime. If they are the good spheres, I should have the proper number of them. I shouldn't have either too little or too much. So I should have exactly the uniqueness statement here is the important thing. It has to be a unique 2-parameter family of spheres. If I have too little, I will not be able to produce them. If I have too much, that means some of these spheres will not be good enough. Okay, so how do we do it? So first of all, this is a procedure which we call general covariant modulated spheres, simply because you deal with, first of all, it's modulation, and you deal with the kernel due to general covariance. And the idea is just to fix the value of certain geometric quantities to be equal to their Kerr value. Okay, so here, these geometric quantities, you have topological 2 spheres in the 4-dimensional spacetime, so they are codimension 2. So you should expect to have 2 circumferential forms, and in particular 2 mean curvatures, so 2 traces of the circumferential form. So what you're going to fix is the trace of the 2 circumferential forms, the 2 mean curvatures, or the 2 expansions sometimes in the language of general relativity. And you're also going to fix a 3rd geometric quantity, a natural one, which is the mass aspect function for experts. For non-experts, it doesn't matter too much if you don't know this quantity. But the important thing is that once you, at least that's going to be your definition of your preferred spheres. And of course, the definition is easy. The difficulty is to prove that they exist. And furthermore, that you get a unique 2-parameter family of them. Okay, so I claim that this is the step. This is what is source modulation in infinite dimension, and in particular, you can see at this stage that because you're constructing spheres, what you expect to get are elliptic systems. In fact, it's elliptic systems. You have to solve 2D elliptic systems if you want to construct these spheres. Okay, so this is where you have modulation in infinite dimensions, so you get PDs rather than OD instead of ODs. Okay, and once you have done this, so this settles if you want, the tracking the final diffeomorphism, and then you still have to track the final mass and final angular momentum. So it turns out that to track the final mass, there was already in the literature. So here I'm going to take these spheres. In fact, maybe let me go back to the picture. At this stage, what I produce are spheres that foliate this last slice, and in particular, the most important sphere here in this last slice is the last sphere S star, because this is the one. In fact, everything starts from that sphere, particular sphere, and this is the one where you want to track the final mass and final angular momentum, because this is the sphere which is most towards the future in your spacetime. So this is the one which you feel most the final parameter. Okay, so the construction starts from this sphere, uses this procedure to foliate this last slice. And now I need to tell you how, based on this sphere, you can compute a mass and an angular momentum, which will track the final mass and final angular momentum. Okay, so for the mass, it turns out that there was already a very good definition called the Hawking mass, which works very well for us. But for the angular momentum, there were lots of definitions in the literature, and it turns out that none of them, in fact, did the job for us. So we came up with yet another definition of angular momentum. And it turns out that as a byproduct of our construction, not only it allows you not only to define the angular momentum, but for the same price, it allows you to track this final axis of symmetry of your final Kerr. In other words, you track something which will converge, even though there is no symmetry in your spacetime, you track something that will converge to the final axis. And I claim that if you don't do that, you cannot actually solve the problem. Okay, and this this definition of angular momentum and tracking of the axis is done using a version of the uniformization theorem. Okay, I'll stop here. Thank you very much.